Right. So I guess the agenda for today, I started talking about Wasserstein-Berry centers, and I briefly mentioned multi-marginal optimal transport on last class. And so I guess that the agenda for today is to continue that discussion. So let me start out talking a little bit about multi-marginal optimal transport. So this is kind of a straightforward generalization of single marginal. So given, let's do it in Rn, although we could do it on Polish spaces, but given mu1 up to mu_m in, let's say, Rn, and a benefit function, which should be a continuous function on Rnm, you would seek to maximize the integral of b d gamma over Rmn, where the maximum is overall I'll write it this way, joint measures gamma with marginals mu1 up to mu_m. And so if you want to, and of course the special case that to keep in mind, well, okay, there are lots of interesting special cases. So the Gangbo-Schweik case was, which actually other people studied before them, but they studied the case where b of x1 up to xm is something like the sum on, let's say, I less than j xi dot xj. Which, of course, that's equivalent to a cost function. Whoops. Decline. Sorry. That's equivalent to a cost function. Maybe I better put my phone into airplane mode or something. C of x1 up to xm would be like the sum on j less than I of xi minus xj squared. I mean, the difference between I guess this, b is not really minus c, but it's rather minus c times the sum on I counting from 1 to m of xi squared. But maybe I better put a half here to make this work. But the integral of these guys against gamma doesn't depend on gamma, because the integral of these guys against gamma only depends on mu_i through mu_m if the marginals are constrained. And so in terms of which one's going to max, you can always add functions of x1 to xm separately to b, and that's not going to change the maximum. Okay. And so there, of course, there's a dual problem to this, analogous to the Kantorovich dual problem, which, and the way to find it is that you would say, well, let me think of these being marginal constraints. And so let me introduce some Lagrange multiplier for each marginal. So I could think of this as the maximum over gamma non-negative on Rm, and then a minimum over some Lagrange multipliers, u1 up to um. These are going to be continuous functions on Rn. And so how do I build the Lagrange multipliers into the problem? I would, let's say, add a sum of terms I counting from 1 to m of integral ui, maybe d mu I, this is probably xi, minus d gamma x1 to xm. And so then I can, let me just do something heuristically formal. But the point is that this objective now, it's sort of bilinear or bilinear or affinely bilinear. Affinely bilinear in gamma on the one hand and u1 up to um on the other. And so if we remember the von Neumann min-max theorem and two-player zero-sum games, this is like a two-player zero-sum game where one player is choosing gamma and the other player is choosing un1 through um. And notice that if say the ith marginal of gamma did not match up with mu, then when I do this min, I would, by suitable choice of ui, I'd be able to make the min go to minus infinity and it wouldn't contribute to the max. So that's why I have this equality here. But according to, and so of course this is always going to be less than or equal to what happens if I interchange the min and the max, because it's like forcing the other player to go first. And whoever has to declare their strategy first is at a disadvantage. So this is always true. And since this is bilinear, if this, and this is like the positive cone in some vector space, and this is some other vector space. If these vector spaces were compact sets, then you'd expect you'd have a rigorous proof that equality holds, and you can hope that equality holds anyways. Somehow, if you could regularize things by adding something growing at infinity to take away the effect of the compactness, growing at infinity in the ui direction where you're trying to minimize, and decaying it, then going to minus infinity at infinity in the gamma direction where you're trying to maximize. So it's natural to expect that equality holds under the interchange of min and max. And let me also, if to interchange the min and max, it's convenient to collect the terms in a slightly different way. And so it's like the integral over Rnm of bx1 up to xm minus the sum of the ui xi's. And that will get integrated against gamma. And then I'll have a bunch of terms of single integrals left over. That bar shouldn't be there. Let me erase it. I guess it doesn't matter because I'm integrating against probability measures, so this is the average. And now I can make the same kind of argument. I'm going to assume that this thing under brace brackets is non-positive, because if it's positive anywhere, by choosing gamma very large at that point, I can make the max go to infinity, and that won't then contribute to the min. So this is the same thing as min. And so this has to be less than 0, which is to say it's the min over ui's such that the sum of the ui's dominates bx1 to bxm. And when this is less than 0, for every choice of the xi's, the maximum is over non-negative measures gamma is going to be equal to 0. And so that's the dual. This is the Kantorovich dual, if you like, of the original max. So I'll summarize. Duality says that the max integral b d gamma over all gammas with fixed marginals is equal to the min integral u1 d mu1 plus um d mu m over all functions u1 plus u2 all the way up to um, such that the sum dominates b. That's the duality statement here. And now if I come back to this benefit function here, which Gangbo and Schweik investigated in 1998, I can say, well, I can say more about this min. So I guess this is an int, but it's actually attained. I mean, I could say more in general as well, but let's focus on that case. I think those of you who've done the assignment that's due tonight know how to show that existence minima exist for things like this. If I think about this constraint, I can do the usual thing. Like let's say I can write so I need some, I guess I should introduce some notation. So let's call UB will be the set of functions U1 to UM that are continuous functions on the space in question, such that U1x1 up to UMXM dominates B. And so I'd like to argue that just as in the Brenier's problem, that I can take all of these UIs to be convex. So without loss of generality, because of this particular form, BI can find an infamizing sequence with each UI convex. And why do you expect that this is possible to do? Well, it's sort of the usual thing. So if you think about UI hat of xi, well, so sorry, let me get rid of the hat for a minute. So I know UI of xi dominates bx1 to xm minus the sum over j different from I, uj xj. And so it dominates the supremum over x1, let's say x minus I in Rn m minus 1, where my convention is that x minus I is basically x1, x2 up to xi minus 1, xi plus 1 up to xm. And so I would call this thing here maybe UI hat of xi. And I might call the vector, I don't know if I'll need this notation or not, but I might call the vector, I might call qi b, if you like, of u1 to um would be just the same guy, u1 up to ui minus 1, and then replace ui by ui hat here, and then ui plus 1 and ui plus 2 all the way up to um. So what the operator QB does is it keeps all of these guys the same except for the ith one, and it replaces the ith guy by this one. And one of the observations that we've just seen is that what the operator QI does is it leaves them all the same except for the one it changes, and it makes that one smaller. And from the point of view of this infamizing problem, smaller is better. And the other observation is that this ui hat, because it's a supremum, also dominates B minus these other guys at any choice of the x's. So so this is in the UB provided the original guys were. Well, maybe even not, but yeah, it's in UB. So it's better from the point of view of the infinite problem, and it's still in the constraint set. So it was a good thing to do. And the other thing to notice about this particular UI is for this particular choice of benefit function, I don't know what to call it, the multilinear benefit function, UI is convex. Because, so if B is multilinear, then UI hat of xi is a soup over stuff parameters. And then there's a term of the form xi inner product x1 plus x2, let's say all the way up to xm. I probably didn't need to include the xi one, so maybe I should subtract it off, minus xi squared. Do I want to do that? Yeah, that's fine. Or maybe it's better to not do that because it maybe confuses the issue. So let's get rid of this xi squared and let me be more careful about what's in here. So this sum goes up to xi minus 1, and then it jumps xi, and then it continues up to xm. And then apart from that, there's the sum over, I could have made this more notationally convenient for myself by choosing I to be 1. The sum over j less than k, but different from I, of the xjk. And then there's finally the sum as j counts from 1 to m, but different from I, j different from I, of the jxj. And so the point is that the only xi dependence is here. And so this is some linear function of xi plus constants that depend on the parameters. But when I take a supremum over a collection of linear functions, that means it's a convex function of xi. Does everyone see that? Are there any questions about that? And so basically, if I iterate these operators qi, so if I define an operator r, let's say rmb, which is basically something like qmb composed with qm minus 1, b composed with all the way down to q2b composed with q1b, what's going to happen is, as I apply these operators qi, is I will take, at each stage, I'm going to improve my candidate for the minimum problem and stay in the constraint set. And I'm going to start out with u1 up to um in the constraint set. And then applying q1, it gives me, this will be like qmb up to q2b. I'll have replaced u1 with something depending on the other guys. And then at the next step, I'll have replaced, so this will be q3b. I'll have replaced u2 by a u2, I don't know what to call, I don't know if hat is the right notation or not, because this, so maybe I should do double hat or something, because this u2 is indeed a hat operator, but it doesn't start from the original guys, it starts from the original guys with u1 replaced by u hat. But anyhow, u1 stays convex, this guy becomes convex, the other guys aren't convex yet, but by the time I get to the end of this guy's convex, this guy's convex, the next guy's convex, and the last guy's convex as well. So maybe my notation is slightly confusing. I don't really mean that I'm iterating this operator, but it's a slight, the arguments are slightly different. So let me call this 2 and 3 and so on up to m. And in fact, if you apply, it's a fact that I don't want to check, but if you apply qi to this guy, it's invariant under another application of any of the QIs, or I think. Okay. So it's enough to look, when I look at this minimization, it's enough to look at least for this choice of benefit function, it's enough to look at convex minimizers, convex functions. And the set of convex functions has nice compactness properties, and so it's not that hard to show the infimum is attained. So that's why I wrote min here. Otherwise, you'd have, so of course, the same procedure works for non-multilinear functions, but then you have some kind of notion of a B-convex M tuple. So you might, if I define UBB to be the set of M tuples U1 up to UM in UB, that are invariant under QI for every I. I claim that this guy is actually in U double B, but it's not terribly important for us. That's true. All right. So I want to analyze for the multilinear benefit function what the maximizers look like in this problem, or equivalently what the minimizers look like in that problem. And so let gamma be a maximizer, and U1 to UM a minimizer. So this is argmax over capital gamma, and this is argmin over, I guess, UB. And so what does it mean? It means that when I take this maximizer and minimizing pair, it means that the integral of B d gamma over Rnm is equal to the sum of, because the min max equal to max min, it equals the sum of the uxi d mu I. And so that's basically like the integral of the sum I counting from 1 to m ui xi against gamma. Because the marginals of this gamma are these mu i's. And so if I write everything on one side, I have that 0 is this integral and the fact that the ui's belong to the constraint set tells me that the integrand is non-negative. So the integrand is non-negative. I'm integrating against non-negative measure. I'm getting 0. And so this non-negative integrand has to vanish gamma almost everywhere. So it has to attain its minimum gamma almost everywhere. So what do you think? What do you think I'm going to do? What do you do with something like that? So let me say what we're looking for. We're looking for some kind of, when m equals 2, we'd be looking, Brenier's theorem would tell us that gamma is supported on the graph of the gradient of a convex function. And we're looking for some kind of analog statement in this case where m is larger than 2. And maybe, I guess I could have motivated, I could have done a better, apart from the Wasserstein-Barry-Center problem, I could have done a better job of motivating this multi-marginal transport. So one way, I mean, about 10 years ago, I had a PhD student, Brendan Pass, who wrote a thesis about this problem. And he liked the following kinds of motivations. So for example, you want to build a house. So you need to hire a contractor and you need to hire various tradespeople, like maybe a plumber, an electrician, maybe some other kinds of trades. And so mu is like a distribution of general contractors. Mu2 is a distribution of plumbers with different skills. Mu m is a distribution of electricians and then some other guys. And somehow the benefit, if you're wanting to build houses, the benefit of a particular contractor working with a particular electrician and a particular plumber depends on the skills of those individuals. And it also maybe depends on them all speaking the same language, especially in Toronto, where a lot of tradespeople don't necessarily speak English. So the benefit of a team where everyone speaks the same language is going to be much greater than the benefit of a team where they don't all speak the same language. Or at least the contractor should speak the same language as all the tradespeople. So that's where this benefit function would come in. And then you want to figure out how to pair the various contractors with plumbers and electricians in order to have the best set of teams to build houses. And that's where this kind of maximum would come in. And then what's the dual minimum is sort of how much do you have to pay the plumber and the electrician and the contractor as a function of their skills in order to incentivize the most appropriate contractor to work with the most appropriate plumber and electrician. So that's somehow the motivation to this kind of problem. And now what I want to study is, what do the set of teams that come out of this kind of problem look like? So how can we identify which contractor will work with which plumber and which electrician on which house? Any suggestions?
We can use the same characterization that the optimal gamma vanishes outside the zero set of this function.
Right. And so what, so there's sort of a natural thing to do in order to exploit that characterization when you're in Rn or on a manifold. So it's a zero set of a non-negative function. So what do we know about the zero set of a non-negative function?
It's a minimum.
It's a minimum, exactly. And what do we know about minima? So what does calculus tell us about minima?
First order, there's
a first order condition and a second order condition.
yes.
Right. The first order condition tells us the derivative vanishes as long as it exists. So for example, if I differentiate with respect to xi, which it's not really a partial derivative, it's a gradient with respect to xi, I'm going to get that dui of xi equals dxi of b. And for the multilinear benefit function, the Gangbo-Schweik one, that's going to be dxi is going to be x2, sorry, it's going to be x1 plus all the way up to xi minus 1 plus xi plus 1 all the way up to xm. And the second order condition is going to tell us that d2 uxi with respect to xi is bigger than d2 xi of b, and since b is multilinear, this is going to be 0. So this is, in some sense, this is telling us convexity of ui, which we already knew, that we could choose ui to be convex. So we don't learn so much new from the second order condition, but we do learn the first order condition, and this holds provided xi is a point of so B is nice and smooth, it's multilinear, but I need xi to be a point of differentiability of ui. And the good news is that convex functions are differentiable Lebesgue almost everywhere. In fact, they're differentiable outside of subsets of codimension 1. So i.e. Lebesgue almost everywhere. All right, so far so good. Now, of course, this is a bit awkward to deal with. And so there's the trick is to add xi to both sides of this equation. And so then you get the sum of x1 plus x2 all the way up to xm. And this sum is independent of I, so that means this is also equal to xj plus grad uj xj for gamma almost every x1 up to xm. So in particular, I guess I could state a theorem if the mu i's are maybe I don't want to state a theorem yet. So, but well, yeah, let me not state a theorem yet. And so so of course, this is also gradient of a function vi, and this is gradient of a function vj, where vi of xi is basically 1/2 x squared, xi squared, plus u of xi. And so we already knew u was convex, v is even more convex. So sometimes you call that 2 uniformly convex or whatever. In particular, the Hessian of vi is equal to the identity matrix plus the Hessian of the ui, and which is non-negative, so it's bigger than the identity. And I can't remember how much I said about Legendre transforms earlier in the game, but if I define v star of y to be the supremum over x in Rn of x dot y minus vx, that's the Legendre transform. And basically this definition is cooked up so that dv star composed with dv of x is equal to x, and dv composed with dv star of y is equal to y almost everywhere, assuming if v is convex. This definition is cooked up so that the gradients of v and v star are inverse maps to each other. And if I differentiate either one of these relationships, like say this one, then what I get is the second derivative of v composed with the second derivative of v star is the identity map. And so since I have a lower bound on the Hessian of v, if I have this global lower bound on the Hessian of v, that implies a global upper bound on the Hessian of v star. So in other words, it implies v star is one Lipschitz with constant 1, or non-expanding, i.e. it's grad v star, rather. Grad v star is 1 Lipschitz, i.e. non-expanding. And so now I have these m convex functions v whose, oh shoot, whose gradient is therefore dvi is invertible on its range. And so when I have these equations like dvi xi equals dvj xj, that implies that I can write xj in the form dvj inverse of dvi xi, where this is a nice Lipschitz map, and this is in its range, so I'm in good shape. In fact, this is a non-expanding map. So here's the theorem that I was going to state that sort of follows from these considerations. If mu1 up to um are Borel probability measures on Rn, and the first one, let's say, is absolutely continuous with respect to Lebesgue, then there exists convex u1 up to um such that if I define fi xi to be xi plus gradient ui at xi, then has a Lipschitz inverse. And so what this equation basically says something like fi xi, let's say f1 x1 equals fj xj for every j, gamma almost everywhere. And so in other words, xj is going to equal fj inverse composed with f1 of x1 for gamma almost all x1 to xm. And so somehow gamma is living on the graph of all of these maps. And gamma is going to be equal to the identity cross f2 inverse composed with f1 cross f3 inverse composed with f1 all the way up to fm inverse composed with f1 push forward of u1. And gamma uniquely maximizes our multi-marginal problem for the bilinear, whatever, bilinear or multilinear surplus. And u1 up to um are convex functions minimizing the dual. So this is kind of a partial analog of Brenier's theorem for the multi-marginal case. Is it clear? And somehow we did the proof before stating the theorem, which when textbooks do that, I hate it. But okay. So basically you use the absolute continuity of the first marginal with respect to Lebesgue to know that grad u1 is differentiable almost everywhere. So f1 is defined mu1 almost everywhere. And I don't really need that for the other guys because I'm breaking the symmetry and writing gamma as a graph over f1. I could write it as a graph over any of the fi's provided mu I was absolutely continuous with respect to Lebesgue measure. Okay, so now we come back to the Wasserstein-Berry center problem. At least in Rn. And so that was, I'm given the same kind of data, given mu1 up to mu(m). That's an n. And lambda1 up to lambda m, let's in non-negative reals. I want to define, I want to seek mu to be the minimizer over all probability measures of the sum I counting from 1 to m, lambda I d2 distance in Rn of mu to mu I. That was the Wasserstein-Berry center problem. And since I can always divide by the sum of the lambda i's, so I might as well normalize the sum of the lambda i's to be 1 without loss of generality. And so just as in the hedonic pricing problem, another way to write this min oh, it's squared. I better square this. Otherwise, it won't be so nice. Is I could also think about minimizing over joint measures gamma on gamma on Rn to the m plus 1, where gamma should have mu1 up to mu(m) as its marginals, but I don't constrain the first marginal. So this could be any mu, and I want to do a minimum over all those mu's. Or to be more explicit, I could say this is min over mu, and then I could write the mu here. And so some other point is that using here, I'm pairing mu with each of the mu i's independently, but using the splitting theorem, what is it called, the disintegration theorem, whenever I pair mu with each of the mu i's independently, I can also pair mu with all of the mu i's together. And so this would be min mu in probability measures on Rn. And then what am I minimizing over? When I do that, I'm minimizing over, it's now an integral over r to the nm plus 1. But I'm writing the variational problems that define the Wasserstein distance squared. And the variational problems that define the Wasserstein distance squared are basically, I want to minimize something like the sum of the x minus xi squared, I counting from 1 up to m. And this would all be with respect to d gamma x, comma, x1, x2 up to xm. And since I'm completely free about what measure mu I want to prescribe, another way of thinking about this is if I can recall that the argmin over Rn of a sum like this, I showed this last class, x minus xi squared is actually equal to just the minimizing point is the Berry center. Right, this is a nice convex function because the lambda i's are non-negative, and so it has a unique min and it's minimized at the Berry center. And here's the Berry center with respect to the weights lambda. So let me So basically what I can do is I can think about trying to, and let's see what happens to the integrand here if I minimize with respect to x for fixed x1 through xm. This integrand is always bigger than what you get when you plug this in for x. Oh, maybe before I do that, let me give me a moment. Yeah, this is what I'm saying is true, but well, I can do it this way. So what's on the left here is a sum as I counts from 1 to m of lambda I x squared minus 2x dot xi plus xi squared. And that's, since the lambda I sum to 1, that's x squared minus, so I should give this a name. Let me call it x super lambda, the barycenter. So this is bigger than x squared minus x barycenter squared minus 2x barycenter, and then the sum of the lambda i's xi's is another copy of x barycenter. And plus the sum of the lambda i's xi squared. And so this is 2 times that. So this guy is always bigger than this guy, and for any choice of the xi's, there is a choice xi, which x lambda, which produces equality. Equality if x equals x lambda. And so this Wasserstein barycenter problem is actually equal to minimization is actually equal to there. So therefore, so by choosing gamma equal to, oh, and again, my notation is a little bit lousy, but let's call this gamma tilde, the guy that has m+1 marginals. So by choosing gamma tilde equal to this is like the identity on our NM cross the mapping x lambda, which is a function of NM variables. We get this integral against gamma tilde. We find that this is always, I guess, bigger than the integral of this function. So this is an integral over r nm+1, and this is an integral over r nm of d gamma. We get this inequality with, so maybe I should call this gamma tilde lambda. Right, so the thing I'm trying to minimize up here is actually minimized by taking the gamma tilde to be this gamma tilde lambda that I've just defined in this way. And then that's actually a multi-marginal problem. So, so the marginals of gamma tilde lambda are mu1 up to mu_m. And so these terms don't depend on how they're correlated. They only depend on the marginals. And so I can forget about them. So equivalently, I'm trying to maximize over gamma in having marginals 1 up to m. And the sum of the lambda is 1 again. So I'm just trying to maximize the integral of x lambda x1 up to xm squared d gamma tilde. And actually, let's see. Right, so this is, so the integrand here, well, let me just call this, in fact, I can call this just gamma, that's better. x1 up to xm. Sorry, I probably would have been notationally better if I'd used different letters for the measure on the RMN and the measure on the RM plus MN plus 1. But this integrand here is, again, it's an integral over RNM, but the x lambda is something rather explicit. It's the sum I counting from 1 to m of xi. And so, so that's the sum I and j counting from 1 to m of lambda I lambda j xi dot xj. And as usual, the terms, the xi squared terms, they only depend on the marginals. They don't depend on gamma. So so it's also equivalently maximize max over gamma in the same set. Integral RNM sum on, let's say, I less than j, lambda I lambda j xi dot xj. And so you may recognize this as the Gangbone-Schweik. Well, if lambda I equals 1 over m for every I, then these constants are all the same and you can pull them out. And then that's the Gangbone-Schweik maximization problem. If they're not, if the lambda i's are not all equal to this, then you can somehow absorb, you can change the mu i's. So you can define mu I tilde to be sort of lambda I times the identity map, push forward mu I. And then it's equivalent to do the max of gamma in gamma 1 mu tilde up to mu m tilde of the integral over r mn, the sum of the xi dot xj. I less than j d gamma. And that's the Gang-Busch-Schweik problem. So somehow finding the optimizer in the Gang-Busch-Schweik problem is equivalent, maybe for these modified measures, is equivalent to solving the Wasserstein-Berry center problem for the original measures. And we sort of characterized what the optimizer in the Gang-Busch-Schweik problem looked like. Any questions about that? And so somehow I've done this all on Rn, but there's the natural generalization to other metric spaces is more generally if D2 metrizes the probability measures on some other Polish space, you can define the Wasserstein-Berry center by the argument no, this is not right. This is not the Wasserstein-Berry center problem. Is find a probability measure I guess we should be looking at P2, the guys that have finite second moments, of the sum I counting from 1 to m of so this Berry center construction, just like the geodesic construction, extends to arbitrary metric spaces, at least if the metric spaces are length spaces. Okay, so I think that's probably about what I wanted to say about Wasserstein-Berry centers. So now I want to turn to these more general metric spaces. So so I want to move now towards so Richie curvature bounds. In general Polish geodesic spaces. And I already sort of said, well, okay, so what do I want to say? So we saw earlier on, since I'm about to start a new topic, if there's any questions, please don't hesitate to ask. So I mentioned what the intuition behind this was last class. I said, that we have one mass distribution, we pair it with another mass distribution, and then we study something like the LP norm. But let me step back from that, and then so in Euclidean space, we saw the LP norms were all, the pth power of the LP norm was convex for all p bigger than 1, and in fact bigger than 1 minus 1 over dimension. But if the Euclidean space had been curved like the sphere, these geodesics would have been separating from each other, so the LP norm would have been even more convex. If it had been curved like hyperbolic space or a saddle, it would have been less convex, maybe non-convex. So there's another perspective on Ricci curvature where we saw that if, so recall if you're in a Riemannian manifold, there was a good notion of geodesic, Gij, and if let's say sigma s and tau t are arc length parametrized geodesics, then we essentially derived earlier in the course that, and so the g distance on the manifold squared between, if these two geodesics pass through the same point at time 0, right? So here they might be, this is like sigma of S, and that's tau t, and they're passing through a common point at 0. And you Taylor expand the Riemannian distance squared around S equals t equals 0. The first order term vanishes, and so do the second order terms because the Riemannian distance squared grows quadratically, not linearly. And so the first nonlinear terms are something like S sigma dot 0 minus t tau dot 0 squared in the metric. And then the next nonlinear correction is something like the next non-zero term in the Taylor expansion is the coefficient of, so let me write it this way, it's some constant times S squared t squared plus plus higher order terms. So order S to the 5th plus t to the 5th as st goes to 0. And that constant, of course, that constant is something like the fourth mixed derivative of this distance at S equals t equals 0. Times probably 1 over 4 choose 2, so probably times 1/6. But if you compute this out squared, if you compute this out, then this turns out to be some multilinear object where I may get the constant wrong again. This is probably something like minus 1/12. Don't quote me on the constant of some multilinear object Rij KL times sigma I dot 0 tau j dot 0. These are the coordinates of the curves on the manifold. Sigma K0 tau tau L0. And this guy here is called the Riemannian curvature. And what it's measuring is in some approximate triangle here. It's measuring how close this triangle is to satisfying the Pythagorean law. So Pythagoras would tell you that the distance between these things is exactly this. So measures deviation from Pythagoras. Leading order deviation from Pythagoras. I mean, at least in the case where these guys are orthogonal to each other, then this would give you the Pythagorean theorem. So the Riemann curvature tensor is measuring something associated with triangles. But you can also take traces of it. So you can, so the so-called Richie curvature, which would be like the metric tensor JL, RIJKL, where I'm summing on J and L here, up to one dimension, and of course G upper JL is the inverse matrix of lower whatever MN. This guy was associated to triangles, but this guy is basically what you do when you take this is a trace. This is like a trace on the second and fourth index. It's a partial trace. It's like you look at all the triangles which contain some given direction, say the direction sigma dot, and you sum over all tau dot, and you could take all tau dot, but the one that's parallel to sigma dot isn't going to contribute anything because Pythagoras holds exactly if we're looking at points on the same geodesic. If we're in one dimension, there is no curvature. And so effectively, it's like you fix sigma dot and you look at all tau dot that are orthogonal to it, and you sum the contributions of these curvatures from the different triangles. And they might add up or they might cancel up. I mean, so the Richie curvature can be 0 even if the Riemann curvature is non-zero, depending on the signs of these terms here. And so somehow we're looking for some kind of analog of this. So if you go to a metric space, you have a good notion, even if we're not a Riemann manifold, we have a good notion of a distance function. And you can imagine looking at triangles and asking how close they are to satisfying something like Pythagoras. And that's what the Alexandrov school in Russia has started to do about in the 1940s or so. And so you can develop a whole theory of what it means to have sectional curvature bounds based on triangles in metric spaces. And those are basically bounds for like the Riemann tensor. But if you want these bounds for these kind of traces, partial traces of the Riemann tensor, this is so-called the Ricci tensor. It's not so clear how to do that in a metric space, because although you can talk about metric triangles, given any 3 points, especially if it's a geodesic space, you can look at the geodesics connecting those 3 points. It's not clear how you should average. You know, I want to look at all the triangles containing one edge, but how am I going to average? How am I going to weight the different triangles? And so it turns out you need a little more structure. So sectional curvature bounds can be formulated in any geodesic space. And my geometry friends tell me that in all the important theorems in geometry, when you need upper curvature bounds, you usually need upper bounds on the sectional curvature. But when you need lower curvature bounds, usually lower bounds on the Ricci curvature suffice. So in other words, you could assume lower bounds on the sectional curvature, but that's often strong. That's more than you need. What you typically need are lower bounds on these averages that make up the Ricci tensor. But to define Ricci bounds requires a notion of averaging. And that's going to be given by fixing a measure, a reference measure, which doesn't need to be a probability measure. Like in Euclidean space, it's Lebesgue's volume. It's going to always be a non-negative measure for us. And we're going to be looking at on a Polish space, XD. And typically it's going to be a Polish geodesic space, but anyways. And so this is somehow the idea, an idea which goes back to Lott, Villani, and Sturm, but it's inspired by the kind of displacement convexity inequalities from my thesis that I showed you last week. So Lott, Villani, and Sturm around, this was actually Lott and Villani was one, so let's say 06, 09, although they came out at the same time, but Lott and Villani's paper took a lot longer to get published. So we can always use the distance d2 u nu, which by definition is, you know, the inf of that's the squared, to metrize the probability measures with second moments. I.e., lift the geometry from points to measures. From points X and capital X to measures mu with second moments. Say compact support would be fine. Or bounded support, whatever. And then you have a good notion of geodesic. As soon as you have a distance, they may not exist. They will exist if it's a geodesic space, but they may not exist otherwise. And so where does this reference measure come in? We use the measure. We wanted to define a notion like the LP norm of a density of a measure. But in a metric space, it's not so clear what the LP norm of the density of a measure is because we don't know what the density of a measure is. You might take one, so a natural reference measure might be the Hausdorff measure. So it could, but need not be. As soon as you have a metric space, there's a notion of Hausdorff to measure for each dimension. Or let's say HN of dimension n. And there's only one non-trivial n. So in other words, if you take n to be too large, hn of x is going to be 0. And if you take n to be too small, hn of x is going to be infinity. And there's precisely one n to the left of which hn of x is infinity and to the right of which hn of x is 0. And we use the reference measure mu, m rather, to define we could define any LP norm. It's convenient to take the case p, the limit as p goes to 1. And so this is going to be, you're going to take the m density of mu and integrate against its logarithm. And that's if mu is absolutely continuous with respect to m and plus infinity else on mu can be anything in P2, I guess. And so sometimes this is because this is a sort of rho log rho entropy. It's reminiscent of what Boltzmann did in the kinetic theory of gases 100 or 200 years ago. And so this is like sometimes called like the Boltzmann or Shannon. Shannon did something like this in information theory. And then the idea would be that convexity bounds properties of S along D2 geodesics in P2X reflect the Richie curvature properties of X. So the triple X DM is called a metric measure space. Or MMS sometimes. So the role of the distance is, it defines geodesics, and the role of optimal transport is to lift the notion of geodesics from points to measures, to probability measures. And the reference measure M defines the entropy. And then it's the convexity properties of the entropy along the D2 geodesics, which reflect the Richie curvature. So for example, well, what could you ask? You could ask, so XDM is said to be, so I guess Sturm talked about curvature dimension conditions. Curvature dimension conditions. XDM is said to have reach a curvature bounded below in dimension infinity if and only if S is okay, D2 geodesically convex along all D2 geodesics. Well, actually, no, not quite in P2X. So let me try to do better. So there's different when you move from a to a manifold, there's actually different notions of convexity. So so this is not quite correct. So recall a function E on a manifold into R is weakly convex, weakly geodesically convex or whatever. If and only if for every X, Y, and M, there exists, or let's say X0, X1 in M, there exists a geodesic I guess I should call this X for consistency of what I was saying up there. A geodesic sigma taking 0, 1 into X, a D geodesic sigma, such that E of sigma S is convex. So weak geodesic convexity asks for it doesn't say that E is going to be convex along all geodesics joining this point. I should have said that sigma of 0 should be X0 and sigma of 1 should be X1. But weak convexity, it asserts the existence of a geodesic joining every pair of points, and it asks for convexity of the entropy along it. And E is strongly geodesically convex if E sigma S is convex for every D geodesic along every D geodesic in XD. And so in a geodesic space, strong geodesic convexity is a stronger notion than weak geodesic convexity because, but in a non-geodesic space, strong geodesic convexity, for example, if you're in a space where there are no geodesics at all, it won't be weakly geodesically convex because there won't be given X0 and X1, there won't be a geodesic joining them. But it will be strongly geodesically convex because there are no geodesics to test the condition under. So this is only stronger than that if you're already in a geodesic space, so that you know geodesics exist between every pair of points. And so, so what this curvature convention CD0 infinity asks is that is for weak D2 geodesic convexity. So it's weakly convex, whatever, right? So it asks, so this asks for every pair of probability measures with finite second moments, there should be a D2 geodesic joining them, along which S is a convex function. And this is basically, I think, where I want to leave it today. So I didn't talk, and if so there's a remark. If D is DG on a Riemannian manifold, Mn, CD0 infinity is equivalent to asking for the Richie curvature to be non-negative. And the role of this, so the zero here is the right-hand side of this Richie curvature bound. So it should be positive definite, a non-negative multiple of the metric. This guy here is a dimensional parameter. And well, since every finite dimension n is less than infinity, it's automatically satisfied. But the idea we're going to talk about starting next week is how to develop analogous notions for CDKN. Where this is a Richie curvature lower bound and this is a dimensional upper bound. Richie lower bound, dimensional upper bound. So if XDM is a Riemannian manifold of dimension n with a Riemannian metric G and the associated volume, then this is going to be CDKN. So here K is going to be a real number and n is probably going to be bigger than 1 and less than infinity. If and only if the Richie tensor on the manifold is bigger than K times the metric tensor and the dimension of the manifold is less than n. And this was, in some sense, the motivation for looking at Richie lower bounds coupled with dimensional upper bounds came from a compactness theorem, a pre-compactness theorem of Gromov that said if you have a sequence of manifolds with a uniform lower bound on the Richie curvature and a uniform upper bound on their dimensions and diameter, I think, then you can extract. Then they're Cauchy in some with respect to a particular metric. So you can imagine that a limit space ought to exist, although it's not so clear what kind of object it is. It turns out it's one of these CDKN spaces. So it's a metric space with a distance and a reference measure. And so that's, I guess, where we'll take it next week. Are there any questions? I am going to pause the recording.